readily reap off the benefits of those tools, and they contact the server, and here as a client you just don't notice that, as a user, I mean, as a human user. You never see the queries at all. They're just generated automatically. Helpful is that we are the reference implementation for web coverage service and also for Inspire WCS in Europe, and that makes life easier. So standards are really helpful there. But let me look a little bit into the architecture. So behind the curtain, what do we hear? The central workhorse is the Rasterman server process, which is multi-parallel, running on one machine with several instances or on any number of machines connected. So we have distributed processing without any central point of failure. And well, when it comes to storage, I said we are database guys. So of course we started putting pixels into the database, and that you can do with PostgreSQL or any other database out there. We also have put pixels into Oracle, IBM DB2, Informix, and so on. Some people then said, okay, actually I'm just interested in the pixels. I don't want to have the overhead of an extra system. So we implemented file-based storage in parallel that does the same thing, but directly on the file system is about 2 times faster. And so we have choices, which you don't realize again on the query interface. It's all the same queries. Fine so far. Then we went to the large data centers, and they said, forget about it. If we talk about 100 terabytes of data, or a petabyte of data, forget about copying that into the database. We said, but we want to do that, because then we can set up our efficient structures for querying. No way they said. Okay? So we had to learn to dive into their existing archives, and that's the part here with the external files, where actually we see the files that sit in some archive as units that logically can form a multidimensional data cube, like a set of TIFF files. And we can address the files and read them, and we also can address meantime inside the files. If there's a tile structure like with TIFF or with HDF, we can exploit that and have a fine granular access. In any case, users never see what's happening down there. They always have the query interface. Oh yes, and then we have an auxiliary tool here, the Federation daemon, that keeps contact with all the instances so that we know where to fetch data from. This is just bare arrays. The geosemantics comes in on top of that, and this is where we find the OGC standards implemented, mostly the web coverage service, but also in particular the web coverage processing service as a georaster query language, and that knows about curvilinear grids and about time versus space and all of these details. So that's the way to access the service. And next, let me look a little bit into that one. So, as we all know, since last millennium, if images are too big, cut them in pieces. So that's what everybody does. And the question is, how do you do that? Well, typically, you would do it like that. You cut it into equal pieces. That is something that you can do, but sometimes it's more efficient to have a different structure. For example, if you want to do time series analysis, and this here is the time axis, then it makes sense to actually stretch these tiles, these partitions, so that, for example, you can answer a time series request with one single disk access. That is, for example, what the NASA data rods approach is doing. So we have per pixel the whole history behind, and so you can do such analysis on a single point over time very quickly. However, in this extreme case, you will have some performance penalty when you do horizontal access. So actually, you never know what's the best just once and for all. You have to find a particular solution for your individual users. That's called database tuning. And therefore, we offer an interface to the administrators or database designers to specify that physical level thingy. So you can say, I'm using this one, area of interest tiling here, where we say, I have a few hotspots. That must go really fast. For the rest of it, just do something meaningful. Okay, in the tiling clause, area of interest, we indicate the areas of interest. And for the rest, well, a tile size of about 1 million cells makes sense. Oh, by the way, use a particular index and a storage, the pure array with compression set-lib applied. So lossless compression. This way we can control what happens down there on the disk without showing that to those users that ask queries. That's the difference, for example, to PostGIS raster, where you see the tiles in the query and you have to write the query in a way that the tiles are processed in the right way. Actually, sometimes it's even difficult. You can get inexact results with that method. So bottom line, you can tile, you can partition the Datacube in any way across any dimension so that it fits your applications best. Well, how do I know that? Number one, ask your customers. Find out if they have preferences. Number two, just look into the logs. Look into the log files and then you can restructure to find the best matching structure for this particular query workload. Oh, which gets me to processing, by the way. So, now we have a query, but we don't have the data. So, we send the query to server A that happens to have dataset A. And dataset B is not that difficult. It's sitting in the same cloud. So, I can ask my fellow. But dataset C actually is sitting in a different data center. This is where we go from parallelization to the federation aspect. Parallelization in a cloud is simple because they're all homogeneous. But what if you have different data centers, different policies, different hardware, and wide area networks? So what we do is actually we look into every query individually and find the best way. Somebody shut me off. Did I say something bad?
You're on again. You want to back up?
On again.
On again? Off again. Trying again?
There you go. Good work.
Ah, okay. Back again. Hello everybody. Recovered.
Another battery there.
Okay. And I have a spare microphone. I had one. Good. So this is a difference, for example, to the map-reduce paradigm. It's not a fixed step of map, then reduce, but each query is optimized individually so as to minimize data transport. And just on the side, this up there is one of our favorite toys. Next year we will go on board a satellite of the European Space Agency and have a Rasterman instance there as part of the Federation. Oh, did I say that? Hadoop? Yes, definitely. It's being used, and by instinct or by reflex, people said Hadoop when somebody mentioned big data in the past. We have heard today that this is seen in a very differentiated way meantime. Actually, Hadoop is an excellent tool for a particular set of problems. Hadoop, however, does not know about the structure. It's about unstructured data. So when I touch the red pixel, it's extremely likely that in the next moment I want to touch the blue pixels as well. That is something that a good architecture will take into account. Hadoop doesn't know about that, so you have to do all this work about tiling and that in the end re-implement some other technology. So why do I need Hadoop for that? If I have an array-aware architecture, I can do all those operations much more efficiently. It has been shown by benchmarks. Okay, and that gets me to the Earth Server initiative, where this is being used. There's an intercontinental activity, actually, which unites Europe, US, and Australia. It's now in its 5th year, and the goal is they're doing agile analytics on 3-dimensional XYT satellite image data cubes and 4-dimensional XYCT climate data cubes. So we have the European Space Agency, Plymouth Marine Laboratory, National Computational Infrastructure Australia doing satellite imagery, and the European Centre for Medium Range Weather Forecast with their climate archive of 87 petabytes climate analysis. So currently what we have exceeded is the 100 terabyte boundary. We are at 144 terabyte currently here, and within a few months we want to have exceeded the petabyte boundary. Here you find rigorously the OGC standards principle implemented. The client-server interface is WCS, WCPS, and a little bit of Web Map Service, using NASA Worldwind as the primary tool for accessing data and then forking off into expert interfaces. So actually this establishes a global federation where everybody who as a minimum supports WCS interfaces can join in, and what users gain is a common information space They don't need to know where the data sit. They can freely combine all the data at their fingertips, and the service, the data centers, will arrange how to process this. Meantime, I'm killing the installation here. Okay. For the data providers, you gain additional data which you don't store, but which become usable for your community, and so you can offer more at no effort. Currently, altogether, we have around about 200 terabyte, and our goal is that next year we get to 3.5 petabyte. So, summarizing, data are something that we can obtain relatively easily. Service quality is a different beast. And I would contend that users will go to the best service ultimately. So why do we go shopping at Amazon? Because they have books that we don't find anywhere else? No. Because they have a very good search, because they have a very easy payment system, and by the way, they have a really rapid delivery. Okay, it's all about service quality. Datacubes, I think, where it makes sense to compile data, might make it much easier than thinking about 1 million images or so. And it unites actually spatial temporal sensor data, image simulation and statistics data under one and the same modeling and querying paradigm, making it easier for users and making it easier to build cross-domain applications. The main arguments, or the main selling points, if you will, I would say is flexibility of the query language, performance and scalability, because the server can do a lot of magic behind, as Keith has pointed out earlier, and tool integration, which allows users to stay in their ecosystem. There is a standard in the make, NDA. It is an extension to SQL with multi-dimensional arrays, has been mentioned earlier as well, and I believe that will be the game changer, because suddenly we get an integration of data and metadata in the same database, in the same information space. And that is something that makes me stop here, because I believe my time is pretty much over. I have some spare slides as well for the next 2 hours, but let's not do that. Thank you for your attention.
Okay, maybe just a couple questions, get back on time track.
Yeah. Yes, please. Raj has to run.
Most discussion talk about processing imagery and satellite imagery. What about the vector data that's in the mobile history, font data? Is there any use case?
So this field of array databases explicitly focuses on arrays. So for vector data, we have other technology available. For example, simple features are available in SQL as well. The interesting question, though, is how to combine that, so that we have integrated queries that go over metadata, vector, and raster data. And that is something that will be achievable with SQL NDA, because now we have everything in the standard that we can do mixed queries. The efficient implementation will be a nice challenge, and I believe there will be quite some interesting research appearing from all those groups that are doing array databases today.
Yes, and then the other option maybe we can convert the vector data into a raster format, actually create image, and then we can use this kind of data.
Right, that is something that we like to do for efficiency reasons, but sometimes users don't want that, because then you tie yourself to a particular resolution when you render that. So actually one research item on our agenda is polygon raster clipping in the database and in n dimensions.
Thank you.
That currently gives us a headache.
Okay, thanks.
Okay, thanks again. And who wants a microphone?
So next we have Mr. Akinori Asahara. He's going to talk to us about the OGC moving features specification. So we had 2 raster presentations there, and I think we're going to have 2 vector data focused presentations, if yours is vector focused. Equal time. No.
Okay. I can, but I know that I have it here. There it is.
Okay, thank you for invitation. I'm Akinori Asahara from Japan. I'm working for Hitachi Limited company. So my work is the research and development of our products. And my main work, one of the main work is the moving feature, that is the moving object, track of data of moving objects. It's the analysis. And now we are trying to standardize the data encoding standard for